Hello, my name is Junkai Huang. Today I'm going to talk about my project about lensless camera imaging. In this video, I will talk about how I build the lensless camera, how to implement the algorithm to reconstruct the image from the raw data captured by the camera, and finally showcase my results and share my thoughts about them. Lensless cameras are cameras with no lens. Instead, they use alternative methods such as diffraction patterns, coded masks, or shadow imaging to capture information about a scene onto a sensor. They often rely on algorithms to reconstruct the final image from the captured data. Compared with conventional cameras, lensless cameras are thinner, more robust, and cheaper. In this project, I built a diffuser camera, one kind of lensless camera. It consists of a sensor and a diffuser with an aperture on it. I removed the lens of a Raspberry Pi camera to expose its sensor. I placed a double-sided Scotch tape in front of the sensor to be the diffuser. And I used the cardboard as the separating material to make sure that the diffuser is placed at the proper distance to the sensor, so that the light passing through the diffuser can converge onto the sensor. And I used duct tape to make an aperture on it. To calibrate the diffuser camera, we need to place a point light in front of it and take a picture. If the diffuser is focused, we could get the clear, irregular wave pattern as shown on the right. This pattern illustrates how the diffuser scatters the point light onto the sensor. We call it point spread function, or PSF. The raw picture taken by the diffuser camera is in a mess. Next, let's talk about how we can use math to reconstruct the picture that we want to see. If we investigate into how diffuser scatters the light, we can easily find that if the light source or the target object is far enough from the camera, the scattering nearly follows two properties, shift invariance and linearity. Because when we shift the point source in a lateral direction, the sensor reading will have a lateral translation correspondingly. And multiple light sources will create an image that equals to the sum of the images that each light source can create. With these properties, we can use a single 2D convolution to represent this scattering process, and we can linearize the image to convert the 2D convolution into a matrix multiplication. Then we just need to solve this minimization problem to get the original image. Naively, we can use gradient descent to solve the minimization problem. We can add Nesterov's momentum to accelerate the gradient descent, and we can even use Vista algorithm, which projects the gradient in a more flexible manner to make the convergence even faster. Here we show the results by the three methods within 100 iterations. We can see that the result from Vista algorithm is the sharpest. Here are more results. We can find that the algorithm works fairly well for simple images with clear contrast between light and dark. But when it comes to the complex image like the third one, a photo of myself, the algorithm is trying to reconstruct the high contrast structures in the image, but the overall result is quite sketchy. That's probably because our PSF resolution is quite low and the method is quite vulnerable to noise. Despite these challenges, we have proven that it is possible to use the diffuser camera to capture and reconstruct an image with a certain level of quality. Looking forward, I'm optimistic about the potential applications of this technology in certain extreme or challenging environments. This project is guided by this great tutorial from UC Berkeley. Thanks for listening.